Hello, everybody, and welcome to this X Live, coming from X-Blue's headquarters just to the west of Paris in Saint-Germain-en-Laye. My name is David Cunningham, and I'm joined by Julien Guichard from our sonar division.
Hello, everyone.
We today are going to spend some time looking at X-Blue's new forward-looking sonar product range and how it can be deployed in navigation and obstacle avoidance applications on crewed and uncrewed vessels. So the format of the event will be, as we've done previously, around a 20-minute discussion presentation with Julien's input, followed by question and answer. So if you've got any questions which arise through the presentation, please post them on the platform, as I'm sure you're very used to doing now, after so many months of confinement and lockdowns. We will do our best to answer all those questions at the end of the presentation. Clearly, if there's any more discussions to have after the event, we'll be very happy to continue. So, into the discussion. So, Julien, maybe you can start by introducing these sonars. What are they, where they come from, and what are they for?
Yeah, absolutely. So first, I have to state that actually in X-Blue, we have a sonar division based in La Ciotat, and this division is building sonars for more than 20 years now, mainly based on three different sonars technology: the SAS technology, the sub-bottom profiling technology, and the multi-beam echo-sounder technology. And we have been for years now developing multi-beam range, mainly dedicated for civilian application. And this multi-beam range is now growing and welcoming two new different sonars, forward-looking sonars, the CPX FLS7 and the CPX FLS5. You may have heard before the FLS 150 and FLS 60 sonars that the same sonars were actually rebranding the name to have a full and complete multi-beam range from civilian application with the CPX and the military or avoidance application with the FLS. So two different FLS products. FLS 7 mainly dedicated for main ship, main surface ship, key assets of the navies, and the FLS 5 mainly for auxiliary fleets, or USB application, unmanned vessels.
Okay, so that's the introduction, the very brief introduction to the products. Maybe now we can dig a little bit deeper. We don't want to go all the way into the technical aspects of the products, but maybe you can just give us a quick overview of the high-level kind of key parameters.
Yeah.
Julien.
And maybe before to go to the parameters, a short update also on the threat they are addressing. On the civilian market, mainly with the CPX FLS5, but both can do the job, we will focus on the safe navigation, making sure your crew and your platform stay safe, taking care about OVNI, about black ice, about objects that are near the surface. Also, with this kind of application, we need to take care of the seabed as well, because we could have seabed going up and be a danger for the crew, danger for the platform. So we also provide what we call a forward-looking bathymetry, the information of the seabed in front of the vessel. And obviously, we have all the military environment and the mine and obstacle avoidance systems that is needed into MCM environments. And here we are taking care about object in all the environment, the surface, the seabed, but within all the water column as well.
Okay. So there's two sonars.
Yeah.
They're intended for navigational safety applications, so situational awareness and detecting foreign objects, let's say, or ice, and then in the MCM environment or in the naval environment, detecting what could be mines in the water column or drifting. Okay, so the two sonars. Now maybe you can give us an insight onto the technical aspects.
Not going all the full numbers and the spec numbers. Anyway, all the numbers I will give here are also in our data sheet on the Xblue website, so you can go back to the website if you want to have the exact data and numbers. Just to have the global idea for the two sonars and that are based on the same technology, sonar technology, which is a Mills cross sonar. So they are composed of two antennas, a vertical antenna and a horizontal antenna, and each antenna is able to do emission and reception, and they can work both at emitting and receiving. Some key number about the specs. For the FLS 7, so the one really used to be on main surface vessel or also to submarine vessels, this one is working at 60 kilohertz, and that give a maximum range of detection about 1 kilometer ahead of the vessel, and the typical range for obstacle we are used to detect and to deal with is about 600 meters in front of the vessel. Looking at the FLS 5, here we have a system that is working at 150 kilohertz central frequency with 30 kilohertz bandwidth, and the maximum range of this sonar will be about 500 meters in front of the vessel, where the typical range with the object we are used to deal with in mine environment is more about 300 or 400 meters in front of the vessel. So that is for the frequency and for the range. Two other key aspects are the coverage, the volume coverage you can address, and the resolution. What are the details you can see into this coverage? For the coverage, a small difference between both systems. The CPX FLS 5 will have a coverage of 120 degree aperture per 120 degree aperture up to 500 meters. And the FLS 7 will have a 90 degree per 90 degree aperture up to 1 kilometer. So that's the field of view actually of the sonar, and the view will make sure to cover. But within this view, we need to speak about the resolution, or how tiny we can detect an object, or how tiny is the resolution of the sonar. For the CPX FLS 5, the resolution is first an angular resolution. What is the minimum swath, the minimum sweep I can make to have the precision within the water column? The angular resolution is 1.6 degree horizontal, and we can have also a 1.6 degree vertical resolution. But we need to speak also about the range resolution, how much I can cut in terms of range the space in front of the vessel. The range resolution for the FLS 5 is 2.5 centimeter, whatever the range you take. That 2.5 for 10 meters range, but that's also 2.5 centimeter at 200 meter range. On the FLS 7, you will get 90 per 90 degree coverage, and within this 90 per 90 degree, you will get also this 1.5 degree resolution in terms of angular resolution, and in terms of range resolution, you will have a 7.5 centimeter range resolution, again, for all range you will get.
Okay, so the aperture is 90 by 90, 120 by 20, 120 by 20 degrees, angular resolution 1.6 and 2.5 and 7.5 centimeter range resolution. Okay, great. That's the high level figures. We don't want to give, I mean, that was plenty of detail, I think, for this context. Hopefully people have an idea what these sonars are, what they're for, and with some knowledge about sonar, have some appreciation of the capacity of a sonar like this. What we're going to do now is have a quick look at an application, the key reference that we have today, which is with the Belgian and Dutch MCM program that many people will be familiar with. Maybe, Julien, you can quickly give us an overview of that project, and so people can understand the context of the deployment of these sonars in that system.
Yes, so here you have the full picture of Xblue being involved into this program. So we are very proud to be part of this project for more than 1 year now, not only on the sonar, but also on the full application that Xblue can deal with. On the sonar side, actually, we are also part of that, and the Belgium and the Royal Netherlands Navies are now doing a completely new build system of different platforms, and they are addressing that with autonomous vessel and manned vessel. This project has been described into the press as the largest and most advanced European contract in the naval robotics for the last 50 years. So we are at Xblue really proud to be part of that and to provide solution to them. The idea of the sonar on board those vessels are mainly protecting the vessel and the crew from risky targets they could have into the minefield.
And so in terms of the challenges in terms of deploying these sonars on the mothership for the FLS-7, on the USVs for the FLS-5, what challenges do they address in each of those cases?
Yeah, actually there are multiple of challenges. First, the top priority is to keep the crew and the vessel safe while they are doing the job into the minefield, because there is a lot of systems. Some of the systems will take care of the seabed, some of the systems will take care of the water column, they will take care of the mines, they will diffuse some of them. And while doing this work, they need to make sure that the surface platform stays safe, are not going into a dangerous target they have not detected or seen. And that's why they have forward-looking sonar mounted, to make avoidance and stay safe. But the target could be everywhere in the water column. They could be in the surface, near the surface, they could be within the water column, they could be directly on the seabed, and they could be drifting, coming and going. So you need to be very conscious about that and take care about the full environment and the full underwater environment. Also, you need to take decisions based on the information you have. And you need to take those decisions quite quickly because you are sailing within this minefield. So you need to make decisions that could bring to a full safety of your platform, to make sure you take an avoidance decision, you take a stop decision, and you need to take that very quickly and sometimes without man on the loop. And then there is autonomous platform. So you need to have a system that can do the full job from the detection to the avoidance, to taking care of the full environment without having man in the loop. So being able to have the full picture of the environment and to deal appropriately based on this environment.
Okay. Okay, that's good. So hopefully now we've got two elements coming here now. You've got an appreciation of the sonar itself, the key parameters of these sonar systems. We've got a little snapshot of a very typical current naval application with manned and unmanned assets, and the potential deployment of forward-looking sonars on these platforms. Maybe what you can help us with now, Julien, is to dig a little bit deeper into the actual technology of the sonar itself, which allows it to address these challenges.
Yeah. So the first idea, as we talked just before, is to make sure we can make detection. But doing detection of target is not the finality. We need to go further. And actually, we cannot only take a sensor. We need to have a full system with different steps to go from the detection to the avoidance. And how we do that embedded into the FLS, both FLS 5 and 7. Actually, we start obviously by detection, taking care of detection within the data of the system. But after this detection, we need to follow up this detection because we will be moving, because the target can be moving, and we need to make sure that in case of multiple targets at the same time, we are following up each of them properly. That's why we provide a tracking system. On top of the detection, we have a tracking, and that allows us to follow tracks and not anymore only detection. Thanks to those tracks, we will get also a lot of data of the target itself. That's the step we call characterization, and we will gather characteristics. Those characteristics could be position, speed, depth into the water column, target strength, the capacity of the target to reflect the acoustic ray, and other various characteristics based on the sonar. And thanks to those different characteristics, that allow the system in an autonomous manner to take a decision on the classification. And here the classification is really a point to state if the target is a risk for my crew on my platform or the target is not a risk. Into the water column, you could have a lot of things. Indeed, you could have target in a minefield that is a real danger for your platform, but you could have mammals, you could have dolphins passing by, you could have stuff in the middle of the water that is not a threat for you and not a threat for the platform. And that also depends on the platform. If you have a big ship, very robust, very strong, maybe a small box into the water column, you will not make an avoidance on that. You want to go straight to continue your mission and not be annoyed by that. But if you are a very small platform, less robust, you may need to take care of that. So actually the classification parameters that allow the customer to state, this is something I want to avoid, this is something I want to go through, is something available also for the user. Thanks to the classification, the targets will be classified as a threat or not as a threat. We will not go further into the classification. We are not a mine hunting sonar. We will not make very detailed processing on the target itself to know if it's round, if it's square or whatever. We will just base that on a MILEC target. Is that something dangerous or not MILEC? I can go through. But the classification is not the last step. Actually, we have a step again, which is called avoidance. Thanks to the information of the navigation we gather at the sonar system, we have the information of the route of the vessel. We know and we can position the target in the situation. And thanks to those two information, we can provide an avoidance route. A route that will make sure you are not going through and you are not passing by the dangerous target. You will avoid it, and why not come back to your original route if we have the route information as well. So all this chain is built to make sure it can go from one step to the other in a fully autonomous manner. And then be mounted on USB system, for instance. But obviously, the main can be still on the loop, an operator can be on the loop and make manual decision. For instance, he could classify an object that have been evaluated as not a risk, could reclassify it as a risk manually, or the opposite, could classify an object he knows a lot, it's a buoy near my harbor, a place I know, I can classify that as a non-threat to make sure I will not make an avoidance on something that looks like a mine, but is not.
Okay, it's really helpful, Julien. So you're describing here the global philosophy of both systems, and actually the built-in capacity of the system to do a lot more than just detect things in the water column, but actually to, in the end, propose a way of avoiding them if the system judges it necessary, having characterized the target. And presumably within the system, there are a number of parameters that can be configured and databases of different threats, which may be applicable in certain environments for certain platforms and so on.
Yeah, and certain Navy's knowledge also of their environment, the threat they can address.
Okay, that's great. So the next thing we want to look at is, this is the global philosophy. How do we make sure that we actually cover the entire water column? How does the sonar operate in the real world, Julien?
Yeah, you're right. All this philosophy works well as soon as you're sure you are making proper detection. At the start, you need to start by detection. And to make sure you're making proper detection, you need to make sure as well you have the full picture. You are covering the full environment. And that's the key, and that's the start of everything. And we need to come back at the reality of the minefield we are addressing there. We are going at sea, we are going with autonomous vessel, and we are in an environment that can change. The seabed can move, the environment can be changing. And we have to deal with this environment and to deal with the targets that are within this environment. The big idea and the big capacity of the sonar we are providing, thanks to the mid-course technology and thanks to the sonar that can reset and reparameter the settings of the swath in live during the sonar run, we have actually the capacity to make different swaths and build what we call the swath sequence, different swaths that will be emitting one after the other during the mission. Those swaths are divided in main 4 categories. The first one is what we call the batty swath. This is the red one you will see on the short picture. This red swath is actually a vertical swath with a 120-degree maximum aperture and with 1.6 degree minimum resolution in terms of angular. This swath will take care to detect the seabed, to know if there is a seabed in front of you, where is the seabed, and if there is no seabed on the environment. Thanks to this information, this seabed information, and actually the forward-looking bathymetry in front of your vessel, first, we can raise an alert thanks to a threshold based on the capacity of the vessel to go through very shallow water, and then raise an alert to make sure you are not going to this seabed and be in danger for the platform and for the crew. That's the first point. Second point, we will use this seabed information, so the depth of the seabed in front of the vessel, to reparameter the swaths that will come later. The full idea is to make sure the swaths are working where they need to work. And the next swath is what we call the panoramic swath. It's a swath that takes care about water column only, meaning we don't want to see the seabed with this swath because the seabed will have a lot of reflection. So that will be very complicated to see the target if we have the full environment at a time. So the panoramic swath is actually a swath that will take care from the surface to the limit of the seabed, thanks to the seabed information I had previously with my BATI swath. And that will be an horizontal swath, so that's the gray one, that will be 90-degree aperture for the FLS 7, 120-degree aperture for the FLS 5. And we'll have what we call prime detection. That's where I will detect for the first time a target that could be a threat or not a threat, but I will have to deal with it and to monitor that. The next swath is what we call the seabed swath. That's the green one, and this green swath will focus only on the seabed. So we will have a detection of the seabed only, not taking care anymore about the water column. On this seabed swath, the idea is to detect only the targets that are close to the seabed or on the seabed. The processing of detection will not be the same between the seabed swath and the target within a seabed with a strong capacity to reflect the acoustic ray, and the process of the detection of a target into the water column. That's not the same thing. So we need to address that separately. And we will address that in the sequence to make sure while sailing, we are not missing any part, to have multiple sequence and multiple shots on water column and seabed. So that allows us to make sure we are not missing any target. Drifting and water column target with the panoramic swath, seabed target with the seabed swath. And then we have what we call the tracking swath, which is actually vertical swath, and that could be multiple swaths at a time with what we call a multi-ping swath. We can send up to 4 different direction swaths at a time with this blue swath, and this direction will be at the position of the target we detected thanks to the panoramic swath. Meaning, after a prime detection, we will have tracking swaths to follow up those targets, up to 4 targets at a time, but we can deal with more than that, just selecting the target we want to follow up. And this will also provide more information on the target, more characteristics, and make sure we are doing the tracking as long as the target is into the coverage of the sonar, obviously. So that's the full idea, and this is working in a fully autonomous manner, without man in the loop and without taking care of environment information to give to the sonar in another manner.
Okay, that's great, Julian. Thanks. So essentially, we've got beam patterns which are pre-configured into the system, and then deployed sequentially to create these swaths to do different functions. One is the BATI swath to give us a narrow view of the seabed ahead.
Yeah.
And then the panoramic swath to give us the full water column in the cone ahead of the vessel. And then another one to look specifically at the seabed ahead of the vessel. And then the tracking swaths when the system's picked out targets that need to be characterized, yeah, then it deploys those automatically, presumably.
Absolutely, automatically, and with reparameter live, yeah, depending of the situation. Seabed is moving, target is moving, everything is reparameterable live during the show, during the run.
Yeah, yeah. Clearly, on a moving platform going forward, it's all very dynamic and,
exactly,
and fast moving.
With stabilization as well.
And so, just to clear, so the sequence of these swaths is configurable, presumably, but comes with some settings or some.
Actually, those swaths are clearly within the system and not parameterable by the user to make sure those swaths are optimal for the sailing speed and for the situation.
Okay.
Those swaths can change depending of the seabed depth you want to cover. If you want to cover only a very limited seabed depth or water column depth, we can re-ensure those swaths to make sure you are focusing on the specific area. But you could be in an environment without seabed, in the full blue, and then you will need to have a different sequence that will be computed into the system to cover the full environment, also almost below you, to make sure you are covering the full blue without seabed.
Yeah. Okay. That's great. Well, that's really interesting. To view the system in that level. Hopefully, we've given a bit of insight into the technology inside these sonars. If there's any questions, obviously, please raise them after this presentation or after the event. So, what about a real live demo, Julien?
Yeah.
So we've seen this beautiful imagery. When could I bring a customer to see the sonar in the water?
So actually, we already have our sonar into water currently. We are doing qualification, validation of the system into the water. And obviously, in the coming months, and we can say that in autumn this year, we will have the capacity to welcome customers to visit us and to assist to live demonstration of our forward-looking sonar on XBlue platform or surface vessel, or we also have the capacity to provide USB XBlue platform and to have forward-looking sonar embedded into this XBlue USB to have the full live demonstration of the system working. With the current situation, we also have the capacity to make completely remote demonstration. So with this kind of camera system, we have the capacity to make demonstration all around the world without the customer coming into France and stay safe at home. So we have plenty of possibilities to show by the end of the year and by this autumn the FLS runnings.
Well, that's great. So let's see if we can't organize a demo for the autumn. And as you say, we've done a number of remote demos with this sort of technology. With Drix and with the acoustic products as well. Well, thank you very much for that small presentation, Julien. Hopefully that's helped to open people's imagination and open people's minds to the technology, the application, and so on. Now, have we got any questions? We're ready to answer questions. Have we got any questions? Our capable team are just lining up the questions, so just stand by, everybody. What have we got? Thanks for the presentation. Are you able to compensate the acoustic ray deformation in the water column?
That's a good question, and obviously all people that works with underwater environments know that actually the acoustic ray does not go straight always into the water column. It depends on the celerity profile, so depth, pressure, temperature, and salinity of the water. And today with the sonar, we do not compensate live the acoustic ray. We compensate only at the sonar level. We have a sensor at the sonar level to make sure we compensate at the emission level. But then the profile and the acoustic propagation is not compensated. But actually, we add inside the system a tool that works also during the live in real time that allow us, with the celerity profile information coming into the sonar, but not measured by the sonar, to provide a map of proper detection or not detection. Meaning, if we think that the sonar goes up to 500 meters forward, and actually the bathymetry and the profile of celerity is not allowing the acoustic ray to go that far, we will raise an alert and provide a map of a blind zone for the sonar to make sure the user knows if he's really covering or not this area.
Okay. So it can be included and can help to, let's say, identify blind spots.
Yeah.
But we can't make those blind spots go away necessarily.
Yeah.
Depending on the environment.
So obviously, there is the capacity of the system to work in a completely autonomous way with no man on the loop, so no display, no HMI, but we have the integration within a system. It could be a combat management system, could be a bridge system for navigation. And when there is man on the loop on bigger vessel, we have the capacity also to provide a dedicated HMI with a dedicated console to have the user having the information of the current situation with a 2D map. And thanks to XBlue ECDIS know-how, we are a ECDIS-like display that will allow a user, which is not a sonar expert, to take the end of the sonar and to have a clear and easy information. And this display can be fully integrated in a bridge environment or CMS environment, depending on the use of the system.
Yeah. Okay, so that leads quite nicely on to the next question that we got, which is whether or not the control and display software of the FLS can be integrated into a bridge system.
Yeah. So indeed, this is clearly the case. We can provide fully own build FLS HMI to be integrated into a bridge system. And on the opposite, we can provide output to be discussed with the customer and with the integrator to have those inputs displayed in a existing environment, let's say ECDIS environment or WebDis environment, for instance.
Okay, so there's clearly there's capacity to do some integration work to make that possible. Here's another question. Hi, can you tell us the update rate for the full 3D coverage?
Oh, for the full 3D coverage, actually, with the sequence I've shown you, this depending of the distance you are looking at, so depending of the sonar, the covering rate with that is about between 0.5 and 1 second, because actually each swath will take more or less 0.5 seconds to be emitting and receiving. And actually we need 2 swaths to cover the full area, panoramic swath and seabed swath. With those 2 swaths, so within 1 second, you are making sure you see the full environment.
Okay, hopefully that's clear. Here's another question. Would the FLS be able to provide detailed mine classification?
So on this topic, actually, that's what the FLS cannot do. It will not provide detailed mine classification. We will only be able to have an evaluation of the risk based on the characteristic and the parameter of the classification. Those FLS are not mine hunting sonar. They are clearly avoidance sonar. So we will not be able to provide the shape exactly of the mine, the color of the mine, or even a nice vignette with a picture of the mine itself. This is not the goal here, and this is not what the sonar will provide.
Okay. Here we go. We've got another question. It's coming. Where is it?
I saw we had a question about environment.
Is there one?
Yeah, we had a question about the environment and how much the environment can change the range of detection.
Okay.
And this is a very good question, because actually this is the key when we speak about range of detection. We need to speak what we want to detect and in which environment. And obviously the environment and the object we want to detect will change a lot the potential detection range. With the number I gave about typical range of detection, for instance, for the FLS 7, 600 meter for forward detection, I was here taking an example of an object of about 60 centimeter diameter with a target strength, so capacity to reflect, of minus 15 dB within the water column, with an environment which is at sea state 3. So quite nice sea state actually already, and the seabed at 50 meters below that, and the sandy seabed. So all those characteristics needs to be taken into account to compute and to specify a range of detection. If you want to compare detection range on the market, you need to compare the detection range thanks to the target you want to detect and thanks to the environment of detection, obviously. If you have a specific environment, specific target, you want to have detection information, detection range information, you can send that to us we have computation tool. We can have also already some retext on this target and provide you the exact detection range for this environment and target.
Okay. Okay, yeah, so that's the mine classification story. What about export constraints?
Yeah.
Export control.
We did not talk about
raised a
that.
little bit.
Yeah, that's a question that needs to be mentioned. Regarding export control, the FLS 5, which comes from our civilian strategy and products that we have been put in the market for years now, this is completely export free, meaning we have no limitation to export the FLS 5. Regarding the FLS 7, with this one have been built delicately for military application and to follow up mil-spec environment as well in terms of shock, in terms of vibration, in terms of EMC, and due also to the performance in terms of range. This one is export controlled, so we will need to have from the French MOD a license to export to external countries.
Okay, so yeah, so the FLS 7, the 60
Export
kilohertz
control.
system is controlled as a military goods, and the FLS 5 is exportable without export license. Yeah. So what about submarine integration? You mentioned that the FLS 60 was depth rated. So the question is,
Absolutely.
to what limit?
So the FLS 7 is able to go and to be mounted on submarine, and the maximum depth it can go is up to 1 kilometer below the surface. Mm-hmm. The FLS 5 here is not made to go underwater. Obviously, it goes up to 20 meters underwater, so it could be mounted on hoisting system, could be mounted on the hull of a surface vessel, but will not be able to go underwater and to be mounted on submarines or UVs.
Okay, yeah, so depth rated to up to 1,000 meters.
Yeah.
So we've got one here about the interface and really the expertise required for the operator. Mm. Is it relevant only for sonar experts, so to speak, or is it accessible and usable by normal people, let's say?
Normal human. Actually, we have been building this really for non-sonar experts, meaning the HMI is not an HMI where you will have the acoustic source working live and you will need to have a very strong experience on sonar environment to make your own detection and so on. This is not the idea. Neither you will have your headphone trying to hear something. This is not the idea. The idea is to have something very easy to play with, very easy to understand for a classic operator, military operator or civil navigation operator, that will have the information easily coming to him and will take also decision quite easily. So no sonar expert on the loop. The idea is not to have a sonar expertise on the target. We are not going to classification very detailed with a sonar expert behind. This is really to make avoidance, to know about the environment you have in front of your vessel.
Mm, okay. Yeah, so the idea is that it's going to be a user-friendly environment that could be handled by anyone with some training, presumably. So here's one. It's a really hard question. This one: can you comment on the false alarm rate?
Yeah, no, that's a proper question. When you want to make good detection, you need to take care to not raise a huge amount of false alarm. Yeah. So actually, we have quite high expectation on false alarm. Obviously, our false alarm rate is really reduced due to two things. First, the quality of our detection system, thanks to the fact that we are monitoring the water column or the seabed, but not both at the same time. So we have detection algorithms that are dedicated to the environment of detection. And then the false alarm is also deeply reduced due to the fact that we are doing tracking on our targets. Meaning even if the detector and they will detect targets that are not existing, so raising false alarm, actually with the tracking system that will track the detection from time to time, the false alarms will be also a lot reduced thanks to the tracking system. So we have a really reduced false alarm rate thanks to those two different parameters. And actually we have for the user what we call a sensitivity parameter that can allow the user to raise the number of false alarms and increase the capacity of detection for specific use when we want to make a very specific detection, for instance.
Okay, so we've got some strong management of that false alarm situation, which is inevitable, and some capacity to adjust it given the situation. Okay, here's one about shock protection. So what's the mil standard shock protection of the FLS 7?
Yeah, so I'm sorry, but I have not in mind this exact mil spec standard of the shock level we are following. Just to give you an idea, the maximum G we can support with the system is up to 200 G vertical, and then we need to still work after this shock.
Okay.
So to give you a rough overview, and obviously the antenna are not supporting this directly. We have mounting system and absorber that allows the system to still run and work after this kind of huge shock, obviously.
Okay. Any more questions? Any more for any more? I think we might be coming to the end of the questions. Just giving one minute just to understand if there's any more questions. No, I think we're done. So is that confirmed? No more questions? Yeah. Okay. No more questions. So that's it then, people. Thank you very much for joining us. Thank you very much, Julien, for spending some time explaining
my pleasure.
Explaining the system.
Thank you to you all for joining today.
I hope you've gathered some information, learned something new. And clearly, if you have any further questions, don't hesitate to contact Julien or Exblue through any other channel. We'll be very happy to answer more questions and get into some discussions with any particular applications that you have in mind for this technology. We'll be doing some more X Lives in the coming months, so keep your eyes peeled for the next events, and we hope to see you then. In the meantime, stay safe, and thanks for being with us today.
Thank you. Goodbye.
Goodbye.